on log scale time drawdown data, and then we have to match this data with type curves. Either if it is confined, like of course it is Theis type curve. If it is semi-confined or leaky curve, then we have to match with Walton's curve. Any one of the curve of Walton's, your data will fit, and then we note down the match point values for different parameters, and then we put it in the equation and we calculate the transmissivity storage coefficient for the aquifer. So what Jacob has done, he has tried to simplify the method of analysis. So just to avoid the matching of curve, he has developed a method very popularly known as Jacob's straight line method. Because of its simplicity, it is also called as field method of data analysis. That while you are conducting your test, you just take a semi-log paper, plot the times on log scale, and then drawdown which you are measuring, you just keep on plotting. Y-axis you show the drawdown, and then time versus drawdown data you plot. So you'll be getting a pattern of that line, and then you join the points which are falling on maximum in a straight line. So you connect by line and draw a straight line. And then you try to determine the slope of that line and slope of line per log cycle in time, and where it cuts the time axis at zero drawdown, that is T0 time we take, and then we put it in the equation and we get the value of what you call transmissivity and storage coefficient. So just a little background for those who are new, I'll just give the equations and then I'll be talking about the recovery method. So these are the two methods which is very important and they are used in the field for evaluation of parameters. So I'll share the screen. So the very first equation which is written is Theis equation in the form of convergent series. This is a Theis equation in terms of convergent series. So what Jacob has noted that for small values of R and large values of T, U is small. This is a preamble of his paper, that he said that if R is small and T is large, then U is small. So the series of terms in this equation will be negligible after first two terms. And what is the first two term? That is a factor 0.5772 minus natural logarithm of u. So I'll explain what this is. What is R? You know what the R is. It is a radial distance between pumping and observation well. And what is T? T is a pumping time. So the condition which he thought, and that is fact, that observation wells are not very far away from the pumping well. As a rule of thumb, where to site the first observation well from the pumping well for the purpose of conducting pumping test, so there is no specific rule that where we are going to place the observation well. But as a rule of thumb, it is said that if your aquifer is suppose 50-meter thick, the formation which is acting as an aquifer and its thickness is, if say it is 50 meter, so your first observation well should be 50-meter away from the pumping well. This is not strictly followed, but it is just a rule of thumb. Suppose your thickness of bed is 100 meter, so you just first well should be placed at this particular distance. Otherwise, there is no thumb rule. Depending upon the capability of aquifer, depending upon the drilling data, we site the observation well. So the distance, this R is not very large. Radial distance between pumping well and observation well is not very large. What is large? Pumping time is large. Pumping time is large. I mean, as somebody has asked, I don't know, in this class or in other class, that what should be the duration of pumping. So in case of non-equilibrium method, the duration of pumping is not defined. It is not defined because we can analyze the data of few hours also just to evaluate the parameters. However, it is important that the pumping duration should be at least 24 hours or 48 hours. Ideally, is a 72 hours is taken as pumping duration. Ideal condition is, it depends on several things, depends on your budget and everything. But the ideal is that at least we should conduct the test for 2-3 days. Okay. So if we are doing it for 48 hours, then it is 2 days. If we are doing it for 72 hours, then it will be 3 days pumping test. And in this particular duration, you don't have to stop the pump for a second also. You have to continuously pump. So obviously the value of T is large. And as I have said that this R is always, most cases R is very small. So if this condition is prevailing, then this well function U will be small. So the series of term in convergent series will be this factor into natural logarithm of U. So as a result, drawdown can be expressed as S is equal to Q upon 4 pi T. This and then natural logarithm of R square 4 T. Here, what is U? U is equal to R square 4 T. So we have written in place of U, the value of U is expressed. And what is R? R is radial distance, S is storage coefficient, and T is transmissivity, and T is the time at which we are doing the matching the curve or whatever we are doing. Pumping time, it is since the pumping began. T is the time since pumping began. So this equation can be expressed as U is equal to 2.3 Q 4 pi T log of 2.25 Tt R square S. So by taking this, by considering this, if we plot drawdown S versus logarithm of time T, it will form a straight line. And then we project this line to S is equal to 0, where the drawdown will become 0. And this T will be T0. This T will be T0. I'll explain here in this graph. So here, what is this axis is? This axis is a log axis, and it is here first log cycle, which is beginning from point 1, then 2, 5, 0.5, and then it is 1. Then the second cycle is 10, third cycle is 100, fourth cycle is 1000. That means that we have a pumping test of about 1000 minutes. A pumping test of 1000 minutes. Now what we have to do, we have to plot time versus drawdown data onto this. Time we are selecting uh, on log scale and drawdown on sample scale. So for every time, we just for 1 minute, for 2 minutes, whatever the timing, it depends at how you have taken the reading. For each time, you plot the drawdown. So where the maximum point falls, you draw a straight line. You draw a straight line, and it is zero drawdown line here. Zero starts from here, so it is zero drawdown line is here. So this line intercept this zero drawdown line at 0.39 minutes, 0.39. So this time is called as t0. What is t0? T0 is time intercept at zero drawdown. Now we have to find out the slope of this line. We have to find out the slope of this line. So how we determine the slope? We determine the slope per log cycle. Okay. So actually in the field what we do, we neglect the first cycle. We are not considering the first cycle. Why we are not considering the data of first cycle? Because the first initial reading of pumping test also reflects the losses which are associated with that particular well. And those two losses are called as formation loss and well loss. So what are the well loss? Well loss is well design, loss in casing, loss in screen, gravel packing, any flaw which is there in the not well, your well is not developed properly. So all this will cause your water level decline faster in initial minutes. So initial reading data and formation loss is because of deviation from laminar flow, because of deviation from laminar flow. So the second cycle or third cycle we take consider. So for this cycle, suppose in this particular graph, it is taken second cycle and starts at 1 minute and lasts till 10 minutes. So interval is 1, 2, 3, 4, 5. So at the beginning of the cycle, what was the drawdown, and at the end of cycle, what is the drawdown? So the difference is delta S. The difference is delta S. Now this is explanation of plots which you have already done in your MSc and all those things. One question, what are the exercises which you have done in this practical class? What are the exercises which you have done in your practical?
The depth to water level exercises, pre-monsoon and post-monsoon period, and the fluctuation between pre-monsoon and post-monsoon. The three
And
exercises have given it.
one second, let me check. Let me check. Because what has happened that up to last you were busy in doing this exam, Have you done any exercise related to precipitation and infiltration and surface hydrograph?
No, sir.
And exercise related to grain size have you done?
No, sir.
Any lab class is left, or I mean, your when is your last teaching? 4th April. You have done only depth to water table contour you have done? 3 point problem you have done? No, triangle that I used to give in your, if you have only three wells, then how you will find out the, but not here? Okay. And hydrogeological cross sections you have done? Okay, I'll take care. I'll see. I'll see. Because what has happened? All this difficulty has arises because initially we were not available for this class because it was GATE, it was NetJRF, and then GSI. So we also wanted you that you appear in all those classes so that duration of teaching has reduced a lot. But anyway, I'll try. I'll try. I'll speak with him. Okay. So this is what I have tried to explain to you. This U is equal to this and this. So when we plot this drawdown versus time on logarithmic scale, we get a straight line. And when we project this straight line at zero drawdown, we get time intercept at zero drawdown. That is known as T0. So in this way, the equation is 2.3q 4 pi t log of 2.25 tt0 r square s. Now this is like this. This is S. S is equal to storage coefficient 2.25 tt0 r square s. Okay. So this is for storage coefficient. This particular equation is developed for storage coefficient. This is for storage coefficient. So here what are the parameters which we need to know to calculate the storage coefficient by Jacob's method? That is transmissivity. You need to know. You need to know the time intercept at zero drawdown, and then you need to know R, distance between observation well and pumping well. So therefore, we don't go straight for this storage coefficient evaluation, but we first evaluate transmissivity by using this formula. T is equal to 2.3q 4 pi delta S. What this delta S is drawdown difference over a log cycle. Drawdown difference over a log cycle. This is what the delta S is. Explanation is written. This is just simply, I've taken this all this from the Todd books. Nothing is new here. A value of t can be obtained by noting that t over t0 is equal to 10. T is equal to 2, t0 is equal to 10. So log of t over t0 will be 1. Therefore, replacing drawdown by delta S, where delta S is drawdown difference per log cycle of time t. So this is the equation which is used for calculation of transmissivity. So we calculate first the transmissivity and then storage coefficient. You yourself has done this exercise in your MSc class. In second semester, you will be doing this again. Several exercises I will give so that you can have familiarity with this method. Now there are softwares also. You just use them and you can get the results. But always it is better. Every time in the field, it is better that we do the things manually and then we can use the software just to see any variation. There are certain difficulties where computer doesn't know what has happened. So If you are doing that mechanic manually, then you will understand, okay, what is the problem which has, suppose there are some deviation in the data. So why that deviation is coming? So that you know from the field that what was happening in the field at during that particular time. So it is always good that we should analyze the data manually, and then if you want to use the software, okay, no problem, you can use that. But it's still hand manual calculations are always good. So, because of this, the procedure is that first we calculate T. Why we first calculate T? Because it is required here. Okay, and then we solve the equation for storage coefficient. There's only one tricky point here is that you should be less than 0.001 to avoid large errors. And when this large errors comes, if your observation wells are distant apart, but normally we don't do that. We don't do that, so it is valid for most of the pumping test. It is valid for most of the pumping test. So the either it is a unconfined aquifer, or it is confined aquifer, or it is semi-confined aquifer. This method, Jacob's modification, is valid for each of them. Jacob's modification is valid for every of these three types of tests. So this is all about the Jacob's method, and I'll switch over to the recovery data because time is short, so we have to do it little faster. So you just tell me what is the recovery and how it happens. Who will tell? Time recovery data analysis. What is this time recovery data analysis? Kumar, you just speak something on this. He's not here. Anybody else? Anyone else? What is the recovery of water level? Hello.
So, yeah, hello.
Yes.
From
Yeah. Yeah. Shabba.
yes, as soon as we stop pumping, the water level tries to come up. That is called recovery.
Yes. Very good. Excellent. Yeah. So as soon as you stop the pump, the water level will rise, and that is called as recovery of water level. So how we can make use of that particular data? Atif, what is the significance of taking recovery data? Why we measure the recovery data? Atif, Khalik, if you are just connecting it, it doesn't matter. I don't keep the record of attendance also. Just yours. I'm keeping it just, but it is never even if it was physical class. I never bothered for this attendance. So if you are not attending, don't attend. But unnecessary, you show here that you are present, and then what is the use of that? If you are not interested, don't attend. Okay. Anyone is for all. If you are not here, just connecting and doing something else is useless. I think that disheartened me.
By recovery analysis, we try to see how fast our well will recover, and that will give us कि मतलब हमारा well आगे फ्यूचर में कितना अच्छा हो सकता है और ईयरली इसका जो ड्रॉडाउन होगा वो कम होगा या ज्यादा होगा.
Hmm. So
ये
okay, okay. So this recovery is important, and we do this recovery because we can utilize this recovery data for evaluation of transmissibility. We can utilize this recovery data for utilization of we can use this recovery data for evaluation of transmissibility, and this that value of transmissivity we get by recovery is considered more accurate, more superior. Why? Because in pumping test, what we are doing, we are just trying to stress the aquifer. We are trying to stress the aquifer. How we are stressing the aquifer? We are stressing the aquifer by what you call pumping. So it is not natural response, but we are trying to pump the water. So in response of that stress of pumping, water is coming to the well and it is going down. But in case of recovery, it is a natural response of the aquifer. You are creating a cavity or a depression, and that is naturally going to fill up by the smooth flow of water. So the data which we obtain by recovery, that is considered superior. That is considered superior. And moreover, why we do this recovery? It provides an independent check on transmissivity data which we have obtained from the pumping test. The second very important point, here there is not no cost are involved. Only what you need depending upon how many wells you have. If you are doing it manually, so the people will be there and they will be measuring the recovery of the water level and they will writing in their book. This is what in recovery you have to do. So there is no pumping, there is no electricity requirement, nothing is required. Only the rise of the water level you have to measure. So this data, Thais has said, it can be utilized, and this diagram illustrates the recovery of water level. So this first segment is a drawdown. This very first segment is drawdown, that you are pumping it, pumping it, pumping it, pumping it, pumping it, and you have pumped it for 48 hours. And the drawdown has 4.9 meter in the well, either it is observation well or it is pumping well. So the drawdown which was recorded in after pumping of what you call 49 48 hours, the drawdown was 4.9 meter. And how we have measured this drawdown? We have measured this with respect to static water level. As soon as you have stopped the pumping, water will start rising. And then you start measuring the water level. As soon as you have shut down your pump, after 1 minute, you just take the recovery. After 2 minutes, 3 minutes, likewise, you measure that how it is coming. So this is a drawdown process, and this is recovery process. And if you see that this well has almost recovered, this well has almost recovered. It is 16 feet here, it is 16 feet here, it is also written. It means it's fully recovered after pumping. Now, how we measure this recovery, how the recovery is calculated. So this recovery is also calculated with respect to static water level. Which water level? Prior to pumping, the water level which was here prior to pumping, the water level which was prior to pumping, same reference is here. Here one term is written residual drawdown. What is residual drawdown? What is left over? Suppose here we are here at this particular time. If you draw the arrow straight here, so it will be coming somewhere here. So still this much is left to recover. Still at this particular point, it is left to recover. So that is called as, so there we call it drawdown, here we call it residual drawdown. So what is left? What is left over to recover? So this is a graph which shows drawdown versus and recovery. Now the data I will show you. This is a standard data which is taken from the Todd's book. and the well was pumping at 2500 meter cube a day, was shut down after 240 minutes after pumping. Thereafter, measurement of S dash and T dash are given in table below. Calculate transmissivity using Theis recovery method. So I just wanted to show you that how we record the data. By this graph, I just want to show you how we measure the recovery. This T dash is the recovery time. This T dash is the recovery time. So we have taken recovery at 1 minute, 2 minutes, 3 minutes, 5 minutes, 7 minutes, 10 minutes. So after 10 minutes, recovery got slow. Initial recovery, well recovers almost 95% of the well. If it is a good aquifer, the well recover 95% of recovery takes in an hour or two. Very fast recovery takes place. And then you see that the timing of the recovery is increased from 2 minutes to 5 minutes, and then 20 minutes, then it is again increased to 30 minutes and 10 minutes interval. So we keep on 60, and then it is increased to 20 minutes, and then it is increased to 40 minutes, and then it is taken up to 180 minutes, and this 0.14 is still left to recover. Is still left to recover. So we keep on adding this time here. We stop the pumping at 240, so this becomes 241, 242, 243 like that. And then we calculate here T over T dash, and then I'll come to the main problem. So recovery test. At the end of pumping test, when the pump is stopped, the water levels in pumping and observation well will begin to rise. This is natural phenomena. As soon as you stop the well, the water level will begin to rise in the pumping well, and the radius of influence of that well, where we measure the water level, that is observation wells. So this is referred to as a recovery of groundwater levels. This particular phenomena is called as recovery of groundwater level. And the measurement of drawdown below the original static water level prior to pumping during recovery period are known as residual drawdowns, that is S dash, that is S dash. So we measure the recovery, and recovery time is recorded as a T dash, and drawdown rising of water level is represented as residual drawdown. So I have already discussed with you that it is always good that we should good practice to measure residual drawdown, because analysis of the data enable transmissivity to be calculated, thereby providing independent check on pumping test results. Also, these costs are nominal in relation to conduct of pumping test. Costs are nominal in relation to conduct pumping tests. I have explained to you what the cost will be, only just you have to measure the water level. The rate of recharge Q to the well during recovery is assumed. The rate of recharge during recovery is assumed to be constant and equal to mean pumping rate. So here this Q is taken same as what was the pumping rate. It is presumed that there is well which was superposed on the pumping well, and it is injecting water at the same Q as we have pumped this, as the same Q as we have pumped it. So this, whereas pumping rates often vary and are difficult to control accurately in the field. It's not the case. We are able to calculate the maintain the pumping rate also in the field by using the instruments like orifice scale, V naught. So we have to be, if actually not here, but I have done it in other places, this pumping test. So we are continuously at the site. We move to the orifice frequently. We move to V notch, At regular interval, we measure the discharge. Is there any variation that is noted? And then you can say that, okay, this is the average pumping rate. But as far as fixing of pumping rate is concerned, it is done accurately. If a well is pumped for a known period of time and then shut down, the drawdown thereafter will be identically the same as if the discharge had been continued. This is the theory when Thais has developed, that when if you stop this, so the drawdown should be there, but it is not there, it is rising. So he presumed that there is a hypothetical recharge well with the same flow, and it is superposed on the discharging well as soon as discharge is shut down. So this is the key point, that the recovery is because it is there is a well which is superposing the discharging well with the same recharge rate as we have pumped it. So from this principle, Thais assured that residual drawdown S dan can be given as S dash is equal to Q over 4 pi T W. This is Thais. This is Thais method. And W dash is U dash is equal to R square S 4 T dash. So T dash is time of recovery and U dash is time of recovery. This is pumping time. This is recovery time. So this is subtracted. This is subtracted from here, and T dash are pumping and recovery time. For R small, again here, T dash large, the well function can be approximated by first two terms of the equation given below. Same thing it is here also as in case of Jacob's method. Here also he said that if the radial distance between observation well and pumping well is the same, small and recovery taken time is large, then U will become small. So only these two terms matter, this and this will matter, and rest will become negligible. So this equation will become S dash is equal to 2.3 Q 4 pi T log of T over T dash, log of T over T dash. So I've already explained to you that the plot of residual drawdown S dash versus logarithm of T over T dash forms a straight line. The slope of the line equal 2.3 Q 4 pi T or 4. So delta S dash here it is become delta S dash. That is residual drawdown, change in residual drawdown over a log cycle. So this is how it is same principle as the Jacob's method was developed, and here only we can calculate transmissivity. No storage coefficient can be calculated. So this is what the Thais recovery method is. So these are the methods, conventional methods, which was developed by earlier workers. So here you cannot add anything, you cannot delete anything. It is just as it was proposed. So either it is Jacob or it is Thais or it is a recovery method. It is all it is given by the worker just to estimate the aquifer parameter. So these two topics are over. Just read it from any hydrogeology book if you are interested. If you are not interested, then it's okay. All right, then we'll see you in next class sometime.